as opposed to a linear function, which is a straight line. So the big thing we want to remember about nonlinear functions as opposed to linear functions is that linear functions have a slope, which is a property of the function itself. So in general, the slope of a line is like how steep it is. And I could put a bunch of points on this line, and you could use like a slope formula to calculate the slope of the line through any of those points. But the steepness of the line doesn't change based on which points I choose, right? Like the steepness of the line is the same regardless of what individual points I look at on it. And so the slope of the line is a property of the function itself and doesn't have anything to do with individual points on the line. I mean, I can use individual points to find it, but which individual points I look at doesn't affect what the slope is. So the rate of change is constant. There's a constant rate of change, which we call the slope of the line. On the other hand, nonlinear functions, we can find the average rate of change between 2 points on the function, but what that average rate of change is depends entirely on which 2 points we choose to calculate it, right? Because depending on which 2 points I draw a line through, we get a different steepness based on where we are on that graph. So we can't like say the slope of a nonlinear function is ... because there's nothing constant in terms of rate of change that we can say about the function itself. It depends entirely on where we are on that graph, what the steepness is. I bring this up mostly because we can use 2 points to find the slope of a linear function, and that will give us an equation for the line, which often people try to transfer over to writing the equation of a nonlinear function using 2 points. And so it's important to remember that that doesn't work. Like we can't like find the slope of a nonlinear function and use it to write an equation because that rate of change is always changing. Questions so far? I see a couple of furrowed brows. We good? Okay. So today we're going to focus just on linear functions. The slope of a linear function there's a lot of different ways of thinking about slope. The definition of the slope of a line is the change in the y value corresponding to a 1 unit increase in the x value. So this isn't typically how we find the slope, but this definition is really helpful for things like interpreting rates of change and graphing lines. So what this means is if I have any old line, and I pick a point, if I move 1 unit to the right and then go back to my line, this distance right here is the slope of the line. So however much y changes when I just move to the right 1 unit on my graph. And again, that corresponds to what we talked about yesterday, the rate of change, right? Remember, the rate of change was the change in the output per 1 unit of the input. So they're exactly the same thing. The only thing we did yesterday that we're not doing today is talk about average rate of change, which varies for nonlinear functions. So then let's talk about the slope formula. Well, we did the slope formula yesterday because the slope formula is exactly the same as the average rate of change formula. So the slope of the line through, well, probably if you've seen this before, you've seen it in terms of x and y, right? The like y2 minus y1 over x2 minus x1 business. And we're going to do exactly the same thing. The formula is exactly the same. We're just going to use function notation. So, and I realize that at this point it probably seems like we're just overcomplicating. Like, why not just use y? But this function notation stuff, this like idea of thinking of it in this way, is sort of the bridge from algebra to calculus. So we have to get that down in order to use all that notation that we'll see in calculus, because it's used everywhere. So everything about calculus is just studying functions. And so we, even though it seems a little bit of overkill right now, it's just the practice that we need to get comfortable with this notation so that we can use it in your future classes. So the formula is going to be exactly the same as the one that you've seen before if you've ever calculated slope. We're just going to use different notation. So the points are going to be x1 is the x-coordinate of my first point, just like it was before. But instead of y1, we're going to say my y value is the function evaluated for an input of x1. So the function we're calling f, and I'm going to evaluate it for an input of x1. That whole symbol represents the output or y value of that point. And then my second point, we'll say that x2 is my x value, and then again, the y value is just the function evaluated for that input. So my function with an input of x2. And if you're not familiar with it, those subscripts, the 1 and the 2, they're just labels. They don't mean anything mathematically. Like, you're not doing any operations. They're just distinguishing the first point from the second point. So far, so good? So then our slope, which, remember from yesterday, we represent with m, is the change in our y values over the change in our x values. So the change in y is just the difference in my y values. So my second y value is f of x2. My first y value is f of x1. And then my x values are x2 and x1. One of the tricky things about this is it looks like I've written the x's twice, right, on the top and the bottom. But on the top, those are really y values. They're outputs because I've applied the function to those x values because of that f in the front. So it's saying the output of the function for that x value, as opposed to in the denominator, it's just the x values themselves. So if we have a line through the point, let's make this like 6, 10, and 1, -5. So what those points are saying, if this is the graph of y equals f of x, there's like 3 different ways I can write each ordered pair. I can write it as 1, -5. I can say this is 1 f of 1. I can say x equals 1 and y equals 5. Like, all of those things mean the same thing. And y is equal to f of 1, which is equal to 5. So the number, it's -5. Damn it. The value of the y coordinate is the same as the symbol f of 1. Those are interchangeable. Good? Let's find a slope. So m equals f of 6 minus f of 1 over 6 minus 1. And again, I could have just gone straight to like taking the y coordinates off the graph, but because I know I'm going to need function notation for the rest of my mathematical life, I'm going to practice it now when I know what the answer should be so that I can get used to it. What is f of 6? Yep, good. It's just the y value of the point with an x value of 6. And then f of 1? Yep. Is the y value of the point with an x value of 1. And then over 6 minus 1. It's like 15 minus, or divided by 5 equals 3. Oh, I'm sorry. That watermark like isn't on my screen. I forget about it every single time. Can you see it? The 3. 3. We're going to graph using the slope and y-intercept. I feel like this is like one of the things ever, like, if people remember anything from high school math, it's like this. So you guys are probably familiar with y equals mx plus b. And all we're doing to change that is, again, putting it in function notation. So, oh, I printed some graph paper for you guys. And for things like tests, pro tip, your cat card is great for a straight edge. You can always have your cat card on a test. And I always make my graphs the right size so that your cat card works perfectly. I like straight lines. You will too when we have to see where they intersect, because if they're not straight. I saw on like the homework that you turned in today, like a lot of you on that last problem on the first page, like drew a graph to see if it was linear, which is a great idea, except if you don't have a grid like your graph is probably, you could make any points look like they line up in a straight line. So like if you had something like this, that probably would have worked great to see if it was linear because your spacing is all even so you can actually see. But in math we say a picture isn't a proof, which basically means that just because something looks a certain way doesn't mean it actually is. So try to get in the habit of drawing straight lines. You'll thank me later. So let's graph f of x equals 3x minus 4. What is my slope?
3 over 1.
Mm-hmm. So 3. And what is my y-intercept? So we're going to write it as a point. And I always have you do it as an ordered pair, mostly because when you say -4, you know what you mean, and I know what you mean. But when you're taking a test and you're like panicking already, you're like, where's -4 on a graph, right? Because it's not like a point. So if we always think of it as a point, then even when we're stressed out and taking a test, like we won't panic and blank on how to find it. So to graph using the slope and y-intercept, well, to graph any line, all we need is 2 points. So it's nice because we already have one, which is 0, -4. 1, 2, 3, 4. It's this point right here. And then we're going to use the slope to find a second point. Remember that the slope is the change in y when x increases by 1 unit. So if we start at the point we know on the graph, and we increase x by 1 unit, so go to the right one, my slope tells me that y increases by 3. So 1, 2, 3. And now I have my 2 points, and I'll draw a straight line through them. If your well-meaning high school teacher got you in the habit of always writing the slope as a fraction, that is fine. However, at this point in your career, we're always going to recognize that the fraction 3 over 1 is equal to the number 3 and simplify it for final answers. So write it as 3 because 3 divided by 1 is 3. You can think of it as like 3 over 1 when you're using it as the slope. You just want to make sure that when you like simplify it in the equation and things like that, that you're dividing by that one. What else? Oh yeah, and so like as far as direction goes, I always go to the right because I find it easier to remember 2 directions than 4. So if you always go to the right, then a positive slope is up and a negative slope is down. It's true you can go left and up. I mean, you can go any which way, but I think it's easier to keep track of right and up and right and down rather than like all 4 combinations. So if you always go right, then the sign of your slope tells you if you're going up or down. Let's do one more of these. So again, my slope is -1/2. And the y-intercept here, 0, 3, good. So 0, 3 is right here. And then what my slope tells me is that, so since my slope is the number -1/2, it means that if I go right 1 unit on this graph, that the y value will decrease by 1/2. So it'll be like right here. However, notice I'll be on the same line if I take 2 steps instead of 1, right? Or 4 steps or 20. And it's a lot easier to use integers than to like try to like count off the fractions, right? So instead of, if it's a fraction like this, instead of like thinking of it as a whole number and then 1 to the right, we can remember that the slope is the change in y over the change in x. And so instead of having to deal with fractions or decimals, we can just say that from this point, when y changes by -1, x changes by +2. So again, always going to the right, I went down because it's negative. So my change in y is -1, and my change in x is 2. And that way you get nice integer points, so you don't have to measure off decimals and fractions. Good? The last thing I want to talk about today is finding intercepts algebraically. So we can look at this graph and say, okay, my y-intercept is 0, 3, and my x-intercept is 7, 0, looks like. No. That's wrong. Because my line's not perfect. See what I say about straight lines? There it is. Okay, there's one. There's the other one. So 6, 0, 0, 3. If your line doesn't go through the right point, just pretend. Make a really big dot. That always solves all the problems. Okay, so we want to talk about how to find these algebraically. One, because if we don't have the graph, it would be kind of a pain to have to draw the graph just to find these points. And we already talked about how graphs aren't always exact, right? And then also because this process to find these intercepts algebraically works for any function. So you find the x-intercept the same way for every single function, not just lines. And you find the y-intercept the same way for every single function, not just lines. So if you know how to do it algebraically, then you can apply it to all the functions we're going to talk about. So what can you tell me about the y-intercept? So any point on the y-axis, what's the same about any point on the y-axis? Not just for this line, but any point. What do all those points have in common? Yeah, the x-coordinate is 0, right? Which means that whatever the y-intercept is, it has to have an x-coordinate of 0. And so if I plug x equals 0 into my function, the output should be the y value of the x, or of the y, I can make words, of the y-intercept. So to find the y-intercept of any function,